In this video, we're going to learn how the complex conjugate relates to the roots of a quadratic equation. Let's just start by stating the relationship. So here it is. If a quadratic equation with real coefficients has a complex root, say z, which is given in the form a plus ib, then the conjugate, which is denoted as z bar and is equal to the same real part but minus the original imaginary part, the opposite sign imaginary part. That conjugate must also be a root. So this right here is the relationship between the complex conjugate and the roots of a quadratic equation. And this is going to be the main idea of this video, which we're going to refer back to solve all of the problems, all of the examples in this video. Here's our first example, and this will just be a straightforward application of this idea here. So the equation x squared minus 2x plus 5 equals 0 has a root z equals 1 plus 2i. What is the other root? Well, this equation right here, that is a quadratic equation with real coefficients. Okay, so this theorem applies then. This says that if we have this case of a quadratic equation with real coefficients, and we have the complex root z equals a plus ib, right here we've got z equals 1 plus 2i, great, then we know that the conjugate z bar equals a minus ib must also be a root. So the other root must be the conjugate. And the conjugate is just given by z bar, which is the real part, the same real part, but then minus that imaginary part. So 1 minus 2i. Just flip the sign of that imaginary part, and there we go. This is the other root. Now this might seem almost too good to be true, like it's too easy. All you do is take the conjugate, flip the sign of that imaginary part, but this is in fact true. Why don't we just verify it in this equation here? If we plug in this other supposed root, we should see that it makes this left-hand side of the equation go to 0. Let's go ahead and do that. So 1 minus 2i squared minus 2 times 1 minus 2i plus 5 equals 0. Let's go ahead and simplify this and see if that's true. We get 1 squared, then minus 2 times 1 times 2i, and then plus the quantity 2i squared. That comes from expanding out this, and then let's distribute that minus 2 over. So minus 2 times 1 is just minus 2, and then minus 2 times minus 2i plus 4i, and then plus 5 should equal 0. And let's just continue simplifying, and we'll see that's the case, that it all simplifies to 0. We get 1, and then minus 4i, and then 2 squared is 4, but I squared is negative 1, so minus 4, and then minus 2 plus 4i plus 5 equals 0. So let's see what cancels out. Here we've got a minus 4i and a plus 4i here, so these will both cancel out. And then here we've got a 1 plus 5, so that's a 6. But here we've got a minus 4 minus 2, so that's a minus 6, and that does indeed equal 0. So yeah, it checks out. This is indeed the other root of the equation. Alright, on to the next example. A quadratic equation with real coefficients has a complex root z equals 9 minus I. What is the value of the other root? Well, just straightforward application of this theorem again. We've got the quadratic equation with real coefficients, and that has a complex root of the form z equals a plus ib. Here we've got z equals 9 minus I. What is the value of the other root? Well, it's just going to be the conjugate, z bar, which just comes from keeping the same real part same real part 9, but flipping the sign of the imaginary part. So 9 plus I. That is the other root. Alright, so let's see another application of that theorem. Here the question is, a quadratic equation with real coefficients has the complex root z equals 2 plus I, and if the coefficient of x squared is 2, then find the equation. So now we're not just finding the other root, but finding the entire equation. But let's just take things one step at a time and start with the immediate implications of this quadratic equation with real coefficients having this complex root z equals 2 plus I. That means the other root is z bar, the conjugate, which is 2 minus I. And we'll use this along the way to get to the equation. First of all, let's just find some equation that has the roots z and z bar. Let's not worry about the coefficient of the x squared yet. Let's just construct an equation that has these two roots. So that'll be our first step. Construct equation having roots z, which is 2 plus I, and z bar, which is 2 minus I. And the most straightforward way to do that is just to go ahead and use these in factors of the equation. So let's go ahead and do that. So our equation will go like this. We'll have x minus the first root, so x minus z, and then times x minus z bar, the second root, is equal to 0. So each of these factors will give us these roots, and now we just have to go ahead and simplify this. So let's go ahead and plug in for z and z bar. So x minus z is 2 plus I times x minus z bar, which is 2 minus I, is equal to 0. Okay, so let's multiply this out. So we get an x squared, then plus an x times the negative of 2 minus I. So why don't we really write this as x squared minus x times 2 minus I, and then minus another x times 2 plus I, then plus minus of 2 plus I times minus of 2 minus I. So the leading minuses will cancel out, and we'll just have plus 2 plus I times 2 minus I is equal to 0. And we'll just go ahead and continue to simplify here. So we get x squared, then multiplying this out, we have minus 2x, then plus ix, then minus 2x, and minus ix, and then multiplying this out, we have plus 2 times 2 is 4, and then minus 2I plus 2I, then minus I squared is supposed to be equal to 0. Alright, let's continue simplifying. So let's see if anything cancels out maybe. So this ix can cancel with the negative ix here, and the minus 2I can cancel with the plus 2I here. And now let's just group up what we have. So we have x squared, then minus 2x makes minus 4x, then plus 4, and then minus I squared, so minus of negative 1, so that's really just plus 1 is equal to 0. So that's x squared minus 4x plus 5 is equal to 0. Okay, great. So we've got an equation, a quadratic equation having roots z equals 2 plus I and z bar equals 2 minus I. Now the only part to worry about is the coefficient of x squared is 2. So that's going to be our second step. We're going to manipulate the equation so that the coefficient of x squared is 2. Alright, So we'll use this as a starting point here. Let's bring that up there. Have x squared minus 4x plus 5 equals 0. And what can we do to this equation so that the coefficient of x squared is 2? Well, right now the coefficient of x squared is 1, so if we just multiply that by 2, we can get it up to 2. So let's go ahead and do that. Let's multiply both sides of the equation, all the terms, by 2, and then we get, let's write down what we're doing over here. Multiply by 2. The result of doing that, we get 2x squared minus 8x plus 10 equals 0. And there we have it, a quadratic equation with real coefficients that has the roots z equals 2 plus I and z bar equals 2 minus I, and the coefficient of x squared is 2. There it is. That is our equation. Alright, here is a final example. And this one seems pretty straightforward off the bat. The equation x squared plus ix equals 0 has a root z equals minus I. What is the other root? Well, it's tempting to say that the other root is just the complex conjugate. That's what we've been doing for this whole video. So it's tempting to say the other root is just a complex conjugate of this complex number. So it keeps the same real part. It doesn't have a real part. So we just flip the sign of the imaginary part and get I. It's tempting to say that. But this would not be correct. And the reason why this is not correct is that the theorem only holds for quadratic equations with real coefficients. But this quadratic equation doesn't have all real coefficients. There's an I right there in the x. That's not a real coefficient. That's an imaginary coefficient. So this theorem does not apply. So what is the other root then? How do we find it? Well, we can just factor this one. Let's just write it out. X squared plus ix equals 0. Just factor out an x to get x times x plus I equals 0. So we've really got two solutions, either x equals 0 or x plus I equals 0. That x plus I equals 0 gives us our root x equals minus I. That's where that root comes from. So then this is our other root. So there we have it. Other root is 0. So the takeaway of this example is just to remember, before you apply that theorem about the complex conjugate being the other root to a quadratic equation, make sure that the quadratic equation has real coefficients. That is a necessary condition in order for the theorem to apply. If you try to apply it to a quadratic equation which doesn't have all real coefficients, then it might lead you to a wrong answer. Great, so now we know how the complex conjugate relates to the roots of quadratic equations with real coefficients. In the future, we'll continue to learn more about complex numbers, including how to plot them in the complex plane.